pulmonary artery, if you have a case of phenyltetralogy, then you have strong vortices here, and your blood flow looks different than what's supposed to happen in the healthy heart. Yeah? And of course, yeah, I can use that data now to see if I have these vortices and how strong they formed, and they're also deforming. You can see that the vessels, it's not just that they are stretching it, the vessels are going to adapt to that. Yeah, and of course what's not supposed to happen is any, yeah, you want to know how the pressure is, how it's forming, how it's developing over time, when do I do surgery. Yeah, if you have a problem, I don't do surgery immediately, because I always have to, yeah, as a doctor, say, well, surgery is dangerous, keeping it that way is dangerous, which one is better? And the more information you have, the better. That's the idea. So, still these images give you some insights, but they're still not looking nice. Okay, let's go back to the textbook. These are images, illustrations actually, that inform medical doctors in an anatomy book, hand-drawn of course, about the flu. Okay? Now, there is a part in computer graphics that's called non-photorealistic rendering or illustrative rendering. So why not just try to get images like that based on the actual data, because it may be very instructive. And in giving you a good overview, I can always go back to the original data, but the heart and or visualization is, how do I get the data compressed in a nice fashion, give you an overview, tell you what's going on, and point you to the ones, to the areas where you want to look more in detail. That's the key issue. So basically, if we have so many streamlines here, and they are all belonging to the same group, to the same partition, we can try to find center lines. We basically take that region, do a medial axis transform, and look for the ones that are pretty much in the center. You could also say I have done my clustering, and I look for a kind of a centroid if I have any kind of metric. And then I take one or two of those as representatives. I draw arrows in here, even showing you with this bending, how it behaves. And for the vortex, I may have a center line, but there are also methods that give you the volume, so I can give you a nice illustration for that. Yeah, I can pick one, it should illustrate. Yeah, and you understand it's not a worm down there, but it's a vortex. And then I can reduce this healthy half from here to this kind of illustration. It's not perfect, we're still close to the data, right? But we think this is a lot more instructive than this one. It's just cleaner, it's less drawing. And if you have an aneurysm, we can show you how the vortices are there and reduce this to that, give you an idea how the flow behaves. And of course, if you're interested in detail, sure, no problem, go back to the original data, but I want to give you an overview first, right? And then you see, well, certain vortices shouldn't be there, and there is this aneurysm, and you are going to be nervous about specifically that wall. Yeah, but it's instructive. So the feedback from the medical doctors was the main advantage is you can detect flow patterns in this data. It's a systematic but fast analysis. It gives reproducible results. It's not so much dependent on the actual doctor or radiologist in front of the screen. And they are looking for predefined combinations of predicates for automatic standardized analysis. And there's another colleague at the neighboring university who is actually going quite interesting far further down this road now. And for clinical praxis, they want to have static images, and they're much easier to use than the animations that I'm using so far, because animations are difficult for humans actually. Yeah, because you have to keep in mind what you saw to still keep in mind the whole movie, because you're not seeing the whole movie. Okay. Since Eckhard is currently teaching things about climate research, let's switch to climate research. That's just some new work that we just did lately. We move to Africa, and we're interested in the Benguela upwelling system. That's an area down here. And what upwelling means, well, there is the appearance of cold water from deeper levels of the sea, and it's important for fishery and biomass production. In a nutshell, what's happening, you have the strong passat winds, and on the southern hemisphere, it goes in western direction. And it's pushing the surface water away from the coast in a very constant fashion. And obviously there is no water coming from the continent, so there would be a hole here, and that's filled by water from below. It gets up. And that you can see that here on the temperature, there is substantially lower temperature. Yeah, Japan is an island, you know, usually the ocean should be at least as warm as the far ocean at the coast. Normally it's even warmer. So it's different, you have this kind of upwelling. And there are several of these upwelling areas, and they are only a small percentage of the overall ocean, like 2–3%, but they're producing 10 to 20% of all the biomass. So they're very important for the fishery. You may know about the Humboldt current in around Chile or so on. There are several of these areas. Yeah? And now the question, of course, is this system changing during climate change? Because that's going to hurt the fishery industry, but it's also a very complicated system here. Biomass production means you are taking carbon dioxide out of the atmosphere, right, to create the biomass, and it's going down into the ocean usually. On the other hand, if this is active, it's creating methane that's released into the atmosphere. So it goes both ways, but still you want to study this. So, and our idea was, and this was just what we did last year, how can we do that? First of all, what's the simulation data? It's one that's some German climate model. You could also take the Japanese or the American ones. Yeah, provided here by the Leipzig Institute for the Baltic Sea Research in Warnemünde. It's a rectangular grid. And of course, if you look at the image, yeah, it probably goes to here, it's looking like that. So part of these cells, also if you go down to the sea level, you can see the height is of course heavily exaggerated. Yeah, they are just masked out. Either you have an irregular grid or you take a regular one and somehow you mask which cells are not fluid. Yeah, and then they do calculating in 20 minutes intervals, but we only get 5-day means for a time pyramid of approximately 12 years. It's about 120 gigabytes. And I can already tell you the next student is working on this now, and he will get out the whole many areas and then looking for 200 years and things like that. But we wanted to do the small things first before we go to the supercomputer, right? Because you want to have the algorithm, the principle working before you parallelize and distribute and things like that. At least we wanted. If you are better in that, okay, fine, go directly to the supercomputer, but usually you want to test your ideas first. So we need the upwelling predicate. That's the basic idea here. So we came up with this idea while in this area, the water is coming from below more than 100 meters. It should get above 50 meters, and at some point it should at least have a 60-degree angle with the z-axis or a 30-degree angle pointing upward. It's just kind of a rule of thumb, and there hasn't been any of these studies so far, so we had to come up with some idea. Yeah, and then test. We calculated, just to give you a few ideas, 123 million Pathlines here, and 7 million show the upwelling. And how does it look like? Well, here is I show you the upwelling. You can see, if you are somewhat interested in computer graphics, we did a little bit also with transparency and kept them less transparent if they just did the upwelling. Yeah? And then we did a split between water coming here from the south, the so-called Benguela current, and there's another current where the water comes in here, over here, because they're so nicely split. Yeah? We're just starting now the discussions. Yeah, we just submitted together with other people from the Climate Research Computing Center short paper, and now we're starting to analyze this. And one of the things that is pretty much known to them, there's a strong seasonal variation. In February, which is the southern summer, right? There's not much going on. And in their winter, that will be our summer, like Japan and Europe here, it's substantially more you can tell right from these images. And of course you can also create a video, yeah, to show that over time. And if we say, well, as a rough estimate, the number of trajectories tells you how much water is transported to the surface. Of course, you can do more processing and be more precise once you got the idea, right? But if you just take the numbers, and now we have 12 years, so we take the means, right, over these 12 years to give you an idea, and then you see, well, even statistically it's significant, there's much going on here and substantially less in the southern winter. So you can actually see this. Yeah? Of course, we haven't done much more. They are calculating all the biomass, so they know exactly the chemical and the biological material that's in there based on the simulation, of course. So you could also look at the actual transport and things like that. I haven't done that. Yeah. Well, some work is upcoming and open for new students. Somehow I have to motivate the guys, right, in class. And there's another thing that the student did, and that's he looked actually for the depths was that, yeah, where the water comes from and how far it goes upward. Yeah, and there's a variation now they didn't know before, because so far they were looking at the upwelling right by the surface temperature, which is very simple and easy to do, but it doesn't tell you if that water comes from about 140 meters or from 110 meters. Yeah? And we're going to analyze this. Yeah? Is this just a feature of that simulation? You have to do more simulations. It's easy, right? But the physicists will tell you, right? Do more observations before you try to, yeah, believe this. Check the code before you try to interpret your results. We learned our lessons, I know. Yeah? So at least I can indicate to you that Pathline predicates can be used for upwelling study. Yeah, known properties like different origin currents can be easily found. Seasonal effects like changing intensity, but also changing origin depths can also be found. And this is of course now interesting, because this is new information for them. They have to interpret it. Yeah, but once again we're hinting at that there is also some other difference. And of course it will be interesting once we run that for 200 or 300 years. Is this changing, yeah, under certain conditions in the climate? What does that mean? Yeah, if it's coming from a deeper level, is it better or worse for fishery and biomass production, because the gas concentrations or the nutrient concentrations may be different? Yeah. So further research is needed to understand some of these effects, and you can tell the method is flexible and we haven't exploited its full potential. I'm doing on time. Well, I'm supposed to get closer. I can do this, but I also can stop here. It depends. It will take another about 10 minutes.
What do professors present that as well, or should we?
It's.
Yes.
You want to hear something on image processing on vector fields? Okay. Well, that's fine. Sure, no problem. Well, the goal is to do pattern detection in vector fields. Okay. And of course, you know how to do pattern detection in scalar fields. I hope I didn't cut out too much of this, because I didn't know exactly the audience, but I can explain a little bit more. So first of all, what's a pattern? Yeah. Well, as a pattern here, we define this in a vector field. It's just some part of another field that is given. So I have a field, and I look for the same thing again. But there may be a set of transformations, like translation obviously, but also scaling and rotation on the field that do not change the pattern. Yeah, so if you have a pattern flow, it goes like this, and I observe flow going like this, if I say, well, this is just rotated, it's fine. Yeah, and of course, you can very flexible set this, and the definition of what you're looking for is up to the user. He may or may not give you a closed formula. He can also give us just a sample and say, okay, this looks interesting. I want to see what's happening again in all my data, in all the time steps. Just go and run for it. So find a pattern independent of translation, scaling, and rotation. Well, the difference between scalar and vector fields, you could underestimate if you're not trained by physicists like him. Because you could say a vector field in 3 dimensions is just 3 scalar fields. It's the x, y, and z component. And then I just do the same thing as you would do in image processing for a color image, right? But there's a small caveat to that, and that's the rotation. If you rotate a color image, the colors are not changing, obviously. If you rotate a vector field, the components of that vector are supposed to change. Yeah, so if I rotate this over there, yeah, it's not looking like that. That's what's happening if you turn around a color field, because that green vector obviously is looking in this direction. And if these are colors, then over here it will have the same colors, meaning the same direction. But that's not a physical rotation. It's supposed to look like that. It should be still tangent. Okay? So I can't do exactly what you would do in image processing, in the typical image processing. So the general rotation actually means I have that inner rotation, and I have an outer rotation, I have a scaling, I have a translation, so I have to take care of both of them, basically. So pretty much we look for every grid point, yeah, and for a finite number of inner scales by cutting out the corresponding part of phi to look if we can match this. Yeah?